Hey friends, welcome back to Candy Code. In this video, we are going to look at minimum maximum of an array using divide and conquer method. But before we proceed, if you haven't subscribed yet and you like what you see, do consider hitting the subscribe button. This encourages YouTube's algorithm in promoting more of our videos to more people out there. Let's dive into the problem statement. Write a function to return the minimum and maximum of a given integer array. For instance, if the given integer array contains 1, 9, 60, minus 8, we need to return the minimum and maximum, that is minus 8 and 60 in this case. The naive approach is to iterate throughout the array and compare each value to find the minimum and maximum in the array. We achieve this by initiating min and max value as array of 0. We will then start comparing the values from index 1 to 7. Since value of array of 1 is not lesser than min value, the min value remains intact, whereas array of 1 is greater than the value of max. We'll update the value of max as 2. We repeat the same for each value in the array. When the value is lesser than the min, we will update the min value. If the value is greater than the value of max, we will update the max variable. At the end, value present in the min and max variable are the required values. Let's look at the algorithm. Let nums be the given input array of integers. It is a pretty straightforward method where we iterate throughout the array and find the minimum and maximum value by comparing the elements. The time complexity is order of n, where n is the length of array nums, and space complexity is order of 1. While analyzing the time complexity of this algorithm, once again we need to concentrate on the number of element comparisons. The frequency count of other operations in this algorithm is of same order as that of element comparisons. When the elements in the num array are polynomials, vectors, very large numbers, or strings of characters, the cost of an element comparison is much higher than the cost of other operations. Therefore, we determine the time mainly by total cost of element comparisons. Straightforward method requires 2 into n minus 1 element comparisons. The best case occurs when the elements are in the increasing order, and the number of element comparisons is n minus 1. The worst case occurs when the elements are in the decreasing order. A divide and conquer algorithm for this problem would proceed by dividing the problem P into smaller sub-problems such that the size of the elements is reduced to either 1 or 2. If n is equal to 1, the max and the min value are initialized to num of I. If the n value is 2, the problem can be solved by making one comparison. Let's dive into the solution approach. Let's assume the given input array nums contains 1, 2, 22, minus 5, 17, minus 8, 31 and 9. At first, we invoke the function call with starting index as 0 and 7. We split this into sub-problems with indices 0, 3 and 4, 7. it is relatively large still, and so we divide it further as 0, 1 and 2, 3. On comparing nums of 0 and nums of 1, we return nums of 0 as min and nums of 1 as max. Similarly, for the indices 2, 3, we return -5 and 22. Now we combine the solutions of the sub-problems by comparing the min and max values obtained in both the calls. We do the same for the remaining nodes. At last, the root node returns the min and max value of the entire array nums. Let's look at the algorithm. We have considered nums to be a global array. The parameters I, j, min and max represents the first index, last index, minimum value and the maximum value respectively. We invoke the function with I value as 0 and j value as 1 lesser than the length of the array nums. Min and max as nums of 0. Since it is a recursive function, we start by defining the base condition, then we divide the problem. At last, we combine the solutions of the sub-problems. Let's look at the time complexity. When the array nums contains only one element, the number of comparisons made is 0. Whereas, if the num array contains two elements, we make one comparison in order to determine the min and the max value. If the nums array contains 3 elements, we make two comparisons to determine the min and max value. If you observe, the time complexity of n is twice the sum of the time complexity of n by 2 added by 2. Here, let's say n as 3. The time complexity is 2 into the time complexity taken for n as 1 added by 2. Since the time complexity when the number of elements is 1 is 0, the time complexity here is 2 into 0 plus 2, which is 2. Let's assume n to be the length of the input array. For n is equal to 1, the time complexity is 0, and when n is 2, the time complexity is 1. For any n value greater than 2, the time complexity is t of n by 2 plus t of n by 2 plus 2. Let's assume n to be a power of 2, that is, n is equal to 2 to the power k, where k is a positive integer. We can write this as t of n is equal to 2 into t of n by 2 plus 2. Now, on further simplifications, we'll obtain 2 to the power k minus 1 into t of 2 added by summation of 2 raised to the power I, where I can range from 1 to k. This can be further reduced to 2 to the power k minus 1 plus 2 to the power k minus 2. Since we can simplify this as 2 to the power k into 2 to the power minus 1 plus 2 to the power k minus 2, as told earlier, the value of n as 2 to the power k. The equation can be further simplified as 3n divided by 2 minus 2. Here is a comparison between the naive approach and the divide and conquer approach. The time complexity taken by the naive approach is order of n, and the time complexity taken by the divide and conquer method is order of n log n. The space complexity for the naive approach is order of 1, while the space complexity for the divide and conquer method is log n. Compared with 2 into n minus 1 comparisons for the straightforward method, this is a saving of 25% in comparisons. It can be shown that no algorithm based on comparisons uses less than 3n by 2 minus 2 comparisons. So, in this sense, the algorithm MinMax using divide and conquer is optimal. But does this imply that MinMax is better in practice? Not necessarily. In terms of storage, the MinMax algorithm using divide and conquer is worst because it requires stack space for I, j, max, min, max1 and min1. Given n elements, there will be log to the base 2n plus 1 levels of recursions, and we need to save 7 values for each recursive call. Don't forget, the return address is also needed. If the comparisons among the elements of the array are much more costlier than the comparisons of the integer variables, then divide and conquer technique has yielded a more efficient algorithm. On the other hand, if this assumption is not true, the technique yields a less efficient algorithm. Thus, divide and conquer strategy is seen to be only a guide to better algorithm design, which may not always succeed. Also, we see that it is sometimes necessary to work out a constants associated with the computing time bound for an algorithm. Both the MinMax and the straightforward MinMax approach are order of n, so the use of symptotic notation is not enough for a discriminator in this situation. Please like and share this video if it helped you. It could help someone else too. The complete solution code is provided in the description below. Don't forget to hit the subscribe button for more videos. Thanks for watching. We'll see you next time.